Hi there, thank you for the invitation. I am Edith Puclla for the part of the community team at Percona. At Percona, we run databases on Kubernetes using Kubernetes operators. They are completely open source, and we have operators for MongoDB, for MySQL, for Percona XtraDB cluster, and for PostgreSQL. And today, I want to show you Kubernetes in a different way, from the side and relevance of the database. We will start from the database with PSQL, and we will go from there to understand what Kubernetes is doing. This is our demo environment, a 3-node PostgreSQL with version 18.3. A cluster is running on GKE, Google Kubernetes Engine. It was deployed using the Percona PostgreSQL operator, which is open source, and you can find it here in the link. The operator handles everything: deployment, scaling, backups, users, and certificates, and more. And instead of installing PostgreSQL configuration, replicas, setting up PG Bouncer manually, we can describe that in a file, in a custom resource definition, and our operator is going to handle all of that. In this talk, we will see everything from two sides: from the side of the database terminal using PSQL, and from the side of Kubernetes using the command kubectl. Before we start, one word that we need to clarify is cluster. In the database world, cluster means your PostgreSQL deployment, your primary and replicas. That is what we have on the left of the slide, 3 PostgreSQL nodes. And on the right, in the Kubernetes world, cluster means the infrastructure itself, the machines that need working, everything running your workloads. In this talk, when I say database cluster, I mean PostgreSQL. And when I say Kubernetes cluster, I mean the infrastructure. Now let's connect to our PostgreSQL database from the database terminal. From the laptop, I run PSQL pointing to that IP. This is the external IP of PG Bouncer, the connection pooler that the operator deploys automatically in front of the database. Now I run a query against PG stat activity to see my own connection. It's like asking to Postgres, who am I from your point of view? And if you look at the client ADTR, it returns 10, 164, 2, and 4 as IP. This is the internal pod IP of PG Bouncer inside the Kubernetes cluster. That is who PostgreSQL sees as a client. So there are 2 PG Bouncer IPs, one for getting from outside and one for taking the PostgreSQL from inside, for talking to PostgreSQL for inside, this one. And listen address as an asterisk, it means that PostgreSQL is listening on all the interfaces. And in a traditional setup, you may restrict this. In Kubernetes, for example, network security, we use network security for this, and it's handled in a different layer. From PSQL, without any kubectl command right now, we can already see what Kubernetes is doing and how it is working. Now from the Kubernetes terminal, the same thing that we saw from PSQL, but from another side. This command lists all the services running in our PostgreSQL operator namespace, kubectl get services -n PostgreSQL operator. And if we see, most of them are cluster IP. They are just reachable. If you see type here, most of them are cluster IP, only reachable from inside the Kubernetes cluster. But cluster 1 PG Bouncer is a load balancer with external IP, 34, 58, 52, and 10. That is exactly the IP we used in the PSQL in the previous slide. PG Bouncer is a connection pooler. Instead of every application creating its own direct connection to Postgres, PG Bouncer manages a small pool of connections and share them. The operator deploys it automatically, and we never brought a config file for this. You can also see cluster 1 primary for the primary node, and we can see cluster 1 replicas for the replicas, and cluster 1 HA for the high availability. All were created automatically by the Percona operator for PostgreSQL. As a database admin, the first question that you are going to have is always, how do I connect? In Kubernetes, the answer depends of where your application is. If it runs inside the Kubernetes cluster, it uses a cluster IP, an internal address only reachable from inside. If it runs outside, like your laptop or external application, you need a load balancer with an external IP. We will see it later. Node port, which is this one, builds on top of cluster IP. It opens a port on every node in the cluster, making it reachable from outside. But it is rarely used directly from Postgres in production. And we have load balancer that builds on top of node port. It puts a cloud load balancer in front and gives you a clean, stable external IP. That is what exactly we used previously. My laptop is outside the Kubernetes cluster, so I needed external IP to connect with PSQL. And gateway and ingress are designed for web traffic, HTTP, and Postgres speaks to its own protocol, so we are not using this here. Okay, the command kubectl describes service, cluster 1 PG bouncer, and our namespace. This command gives us the full detail of the PG bouncer service. Look at the IP. There are two, the one who finished in 63 and the one who finished in 10. This one. Okay, the one who finished in 63 is the cluster IP, the external address only reachable from inside the Kubernetes cluster. And the one who finished in 10 is the load balancer external IP. That is the one we used from our laptop with PSQL. And if we see the endpoints, we have 3 endpoints here. These are the 3 PG bouncer pods running inside the Kubernetes cluster. Remember the client address for Postgres showed before with pgstat activity. There we have an IP like 10, 164, 2, and 4. So this is one of the 3 PG bouncers pods IP listed in the endpoint. This one. Okay, and let's look at the labels of this service. These are all the labels that we have. And if we see, it's a app Kubernetes IO managed by the Percona PostgreSQL operator. Everything here was created and managed by this operator. And we are still in PSQL, and now we will query pgstat replication. This view only exists on the primary node. This shows me all the replicas connected to the primary for replication. Look at the replication name column in this part. The application column here. We have cluster instance with this name, and we have cluster instance RSAT. There are 2. And there are not host names I configure manually. These are the Kubernetes pod names of my 2 replicas PostgreSQL pods. So from inside the database, without any kubectl command, I can see the 2 names. I can see the names of the Kubernetes pods replicating from its primary. And notice the client ADDR is empty. It means the replication between pods happen over the internal Kubernetes network. Now let's talk about where our data lives. In Kubernetes, data is stored on persistent volumes, this that exists independently from your database pod. If the pod dies, the data stays safe. Our PostgreSQL pod get access to that disk through the persistent volume claim, also called as a PVC. We don't create this disk manually, but we declare it, for example, I need 1 gigabyte of storage, and Kubernetes will provision that for us. And CSI means Container Storage Interface, and it connects Kubernetes to the storage infrastructure. If we are on AWS, Azure, GKE, or VMware, we can use the same Kubernetes commands everywhere. CSI, which is a Container Storage Interface, will handle it for us. Now we are in GKE, so our CSI driver talks to Google Persistent Disk, and we will see this in the next slide. Now, from the database terminal, we will connect as a PostgreSQL super user. One point that I want to highlight here is that to connect for Postgres super user, we need to change the custom resource definition. So we need to add the user Postgres and give it the high privilege as a super user, and then apply again the custom resource definition, and we are going to be able to use the Postgres user as a super user. So now I connected with this, with Postgres super user, and I run show data directory. It returns PG data PG18. That path, PG data, is not just a folder on the server. It is a persistent volume mounted into this pod. And if we run show temp table spaces, which is empty, PostgreSQL is using the default temp location inside PG data. A table spaces is basically a location on this where PostgreSQL stores database objects. And PG table space show only PG default global and PG default. Just the two default namespaces. There is no custom table spaces created. This is important for DBAs. In Kubernetes, you don't create custom table spaces pointing to different local paths. The storage is managed through PVC, persistent volume claims. And PG data is the PVC mounted into the pod. Now let's see inside of these pods from the Kubernetes terminal. If I run kubectl get pods and I look for the labels of these pods as PG, I have 3 of them, and I will describe the first one. I scroll to the section of volumes, and there are 3 volumes attached to this pod, as you can see. 1 serve volume, Postgres data, and database container info. Yeah. So the serve volume is a projected volume. It pulls in 2 serves, cert1 cluster cert and cert1 replication cert. These are the TLS certificates that keep replication secure. And the important one for us is a database pool, is PostgreSQL data, this one. The type is persistent volume claim. And the claim name is cluster1 instance RSAT PG data. That is the actual disk where PostgreSQL stores your data. It is mounted into the pod by name. And that name is what keeps your data attached to the right instance even after the pod is restarted. So from the database side, you just see the database directory, but from the Kubernetes side, you can see exactly which PVC is attaching to it and how it is wired into the pod. Okay, let's see from the Kubernetes terminal. This command lists all the persistent volume claims in our namespace. You can see 1 PVC per PostgreSQL instance. Each pod has its own dedicated disk. They don't share storage, just like we will not share a data directory between 2 PostgreSQL instances. There is also a PostgreSQL 1 repo, this one. That is the disk of PG Backrest backup. PG Backrest is the backup tool that the Percona operator uses to handle the PostgreSQL backups. And all are with status bound in this one. That means that each disk is attached and ready. All are read-write ones. Read-write runs are this part. Only one pod can write it to a time. And all use standard read-write only. In this. Yeah, this one. Standard read-write only, which is the default GKE storage class. Okay, now let's go deeper into the PVC. I will get the spec of the cluster 1 instance, the first one that we listed before, and it shows storage 1 gigabyte. That is exactly what I declared in the custom resource. Now we have a storage class name as well as the standard read write only. I never specify this in the custom resource. Kubernetes picked this default storage class automatically. And access mode, read write once. Only one pod can write to disk at a time, like we said in the previous slide. And volume name, which is PVC and this one, volume name. This is the ID of the real Google persistent disk that was provisioning automatically on GKE. Now, if we look at the storage classes, standard, if we list the storage classes, we kubectl get storage classes, we are going to see standard read write O, this one as a default, and it uses the PD CSI storage GKE IO. Remember the CSI from the previous slide. So the CSI driver is the bridge between the Kubernetes and Google Disk infrastructure. I only declare storage for 1 gigabyte in my custom resource. Kubernetes uses the default storage class, which is this one. The CSI driver talked to Google, and a real disk was created automatically. And now let's talk about pods. We have been seeing pods everywhere, but what exactly is a pod? A pod is a group of containers managed together, like a little box in Kubernetes that is used to keep all things together. Most pods have only one container, but our PostgreSQL pods have 4. And I will show you that in the next slide. And if we look at the diagram, everything inside that outer dashes box is a pod. The resource constraint boundary means CPU and memory. Limits apply to the whole pod. All the containers inside share these resources together. And the volumes bar at the bottom is the important part for us. All containers in the pod share the same volumes. That is how piggyback REST can read the PostgreSQL data files, the same pod and same volumes. Each container has its own image and its own file system, but the network and the volumes, they travel together. Let's see how these containers looks. If I run kubectl get pods and -l and the pods who start with label PG and in our namespaces, and I can see my 3 instances here, and all of them has 4 of 4 if you see in ready. So it means 4 containers running and 4 containers are ready. I pick up one pod, the first one, and I will ask what containers are inside you. So the command is kubectl get pods, and I will list just the containers with that command. So the name of the containers are database, replication cert copy, pgbackres, and pgbackres config. From the database side, I just connect to the PostgreSQL and run my queries, and I have no idea any of this is happening from the database. But from the Kubernetes side, I can see the whole team, like these containers, are working together, running, replicating, and back up. And next, I will show you what happened when one of these containers at the pod disappears or fails. So the pod, let's see the pod crashes or catches a fire. What happened? Kubernetes is built around one idea: recover fast and automatically rather than trying to prevent failures. If a container inside the pod fails, Kubernetes restarted it, but just that container, not the whole pod. If the entire pod fails, or the node it was running also dies, Kubernetes recreate a pod. And because we are using a stateful set, it comes back with the same network address and the same persistent storage attached. And our data is gonna still there. A stateful set knows nothing about PostgreSQL. It knows how to recreate a pod, but it doesn't know if that pod should be a primary of a replica. This is where the Percona operator comes in. The operator understands the database role and it's gonna handle the recovery correctly. So what the operator on top of Kubernetes does? Kubernetes gives you pods, stateful set services, storage, and more. The operator takes this and assembles them into a real database service. And it lets you to describe what you want in a database terms. The way we talk to our operator is through the custom resource. That is just a YAML file that extends Kubernetes with new objects types. In our case, a PostgreSQL cluster object. When I change something in the custom resource definition, the operator control loop notices the difference between what I declared and what is running actually in the cluster. And it's gonna reconcile the changes. The operator can also take over the stateful set when it comes to recreating pods. So it is the operator, not Kubernetes, deciding how a failed primary gets replaced. And let's talk about logs. As a DBA, you are used to PostgreSQL writing logs on files or on disk, a long directory, long files, log files and log rotation. On Kubernetes, that changed. Kubernetes writes to stdout and stdr, and Kubernetes picks up and stores it in the node where the pod is running. Those logs live on the node, not in some central place. Kubernetes does not aggregate logs across the cluster between the pods by default. If that node crashes, the logs are gone. So for production environments, you want to look like tools like Fluent or Kubetail sitting on top or collect to aggregate this log across the whole Kubernetes cluster. Let's see that from the database terminal. We are going to log in the database with a super user and execute the query show log destination. The answer is stdr. PostgreSQL is configured to write its log to stdr, not into the file. And the operator set this up that way specifically so Kubernetes can collect these logs. I also ran show log rotation size, and it returns 0. No log rotation because there are no logs files to rotate. Kubernetes is handling all of that. Now let's see from the Kubernetes terminal. If we see kubectl get pods, and we check one of the logs, for that kubectl logs and the name of the pods, of the pod, and we are going to list the last 10 lines. And every single line, as you can see, says the same thing. I'm cluster 1 instance, a secondary, and follow a leader cluster, which is another pod. This is a Patroni token. Patroni is the high availability component running inside your database container, and it is reporting its own role every 10 seconds. From here, I can see immediately which pod is the primary and which ones are replicas, without connecting to the database at all. Okay, so let's bring everything together. A database on Kubernetes is not just a container running on PostgreSQL. It is a package, a container images for the database engine and all the supporting software like Patroni, piggyback REST, the certificates tool, plus an operator that knows how to run and recover a real database cluster. The operator and the Kubernetes cluster controller are always watching. At initial deployment, they build everything to match what we declare and reconcile the changes. If something fails, they work to get it back as a target state. We don't need to do it manually. We describe what we want, and the system is going to drive itself there. Your database processes run in pods, groups of containers managed together. You saw that with our 4 containers, the database, the replication certificates, piggyback and piggyback they live and die together as a unit. Your data lives on persistent volumes mounted into each pod through the persistent volume claim, PVCs. That is why when a pod is recreated after a failure, it finds its data exactly where it left. The pod is gone, but the disk is still surviving. When things fail, containers restart, pods get recreated, and your logs are sitting on each Kubernetes node, ready for kubectl log command when you need to debug. And that's the whole picture from the database out. If you want to try it for yourself, you can just explore our repository in GitHub, which is Percona PostgreSQL operator. And if you like, you try and you like, you have feedback, we have an open roadmap. You can also explore that and add issues or feedback on that. And if you like it, also you can start our repo. And if you need more information and more details in configurations and more, you can also read our documentation in Percona docs. It's very well detailed, so it's easy to follow. And if you have more questions as well, join to our community in Percona, in forums.percona.com. And that's it for today. Thank you so much.